Hello and welcome to the webinar Biokinetics and Time-Integrated Activity Introduction to Pharmacokinetic Modeling. My name is Gerhard Glatting and I'm a medical physicist at Ulm University in Germany. My research focuses on implementing pharmacokinetic modeling for dosimetry and treatment planning. I have nothing relevant to be disclosed. After briefly introducing the connection between internal radiation dosimetry and pharmacokinetic modeling, I will concentrate on the workflow of time-activity curve fitting, including input data, input models, model selection, and output data. So, what is the connection between internal radiation dosimetry and pharmacokinetic modeling? The absorbed dose in a patient depends on the number of decays in the source region S. The number of decays can be calculated by the integration over the time-dependent activity, and the time dependency of the activity is governed by pharmacokinetics. Therefore, we need accurate and precise time-integrated activity calculations for accurate and precise dosimetry. Two terms with a clear, distinct meaning are used in radiopharmaceutical therapy. Pharmacokinetics, which describes what the body does to the drug, and pharmacodynamics, which describes what the drug does to the body. Pharmacokinetics is due to the absorption, distribution, metabolization, and excretion of the radiopharmaceutical. Pharmacodynamics is caused, for example, due to tumor cell killing. How is time-integrated activity determined? We have some measurements of the activity at different time points, and then to integrate from time 0 to infinity, we have to interpolate somehow the measured data, and usually more challenging to extrapolate from time 0 to the first measurement and from the last time point till infinity. This can be done in many different ways, which is why we need pharmacokinetic modeling. Obviously, the three shown curves will result in different areas under the curves or time-integrated activities. What is the problem? The problem is the sparse data. If we could measure the activity every minute until the activity has decayed up to 99%, pharmacokinetic modeling would not be relevant. However, in nuclear medicine we have sparse data. This is why pharmacokinetic modeling is essential for accurate and precise results. But now, what does accurate and precise mean? A result is accurate if there is no bias or systematic error, for example, due to measurement errors or using wrong fitting functions. A result is precise if there is a low uncertainty for the result. The result shown in the last line immediately tells us that the result is not trustworthy due to the large standard deviation. Worst case, results are presented without uncertainty, although one already learns in school physics that the result without uncertainty is not a result at all. In the past, I liked to show this slide as I thought of this as a sequence. First data, then models, and finally results. However, as you will see in the next slide, the model can also be seen as an input. It is not a sequence as shown in this slide. Data and models are inputs which are both processed. Therefore, do not optimize only the data part. On the left side is a graph showing data points and the possible fit curve, and on the right is shown a scheme for the processing. There are two inputs, data and models, and the processing needs a model selection to obtain a trustable result. Note that the garbage in, garbage out paradigm applies to both data and models. The real world is never perfect, therefore optimize both. Input data. Quantitative time-activity data are essential input. Their uncertainty, number, and schedule are relevant to the accuracy and precision of the time-integrated activity. Specific data, such as anatomical, demographic, and biomarker values and physiological parameters, can be used in particular models. For example, these parameters can be used in physiologically based pharmacokinetic models and in artificial intelligence models. Finally, population data can also be used. These comprise all the data above and reflect the distribution of the parameters of interest in the patient population. This distribution knowledge can be integrated into determining the time activity curves of individual patients and thus helps improve the accuracy and precision of the results. Such population pharmacokinetic methods are presented in the respective webinar. There are more data that are not mentioned on this slide. These are the data specifying the used fit algorithm, for example, the used start parameters for fitting and the set tolerances. The number of sampling points and the schedule are essential. There is a trade-off between accuracy and cost, which includes, for example, the patient load and staff working time and expense. A rule of thumb is to use 3 sampling points in an adequate schedule per exponential. However, finding the number of needed exponentials is not trivial. Lower numbers of measurements are possible using a priori information. This prior information can consist of the population data already mentioned, but also of structural knowledge like knowing already the number of exponentials needed in the fit function. Input models. Trapezoidal integration is a model-independent approach. It is a purely mathematical approach, and the extrapolation to infinity leads to a high and unknown uncertainty when calculating the time-integrated activity. Sums of exponential functions are often used as they are simple and do not need to specify a physiological structure behind the observed kinetics. Compartmental models also do not have a strict physiological basis. However, a known structure is assumed. An example is shown in the next slides. Physiological models are also compartmental models. However, they identify the compartments with actual body spaces. Actual transfer and flow rates are employed, so they are more complex but can be used for predictions. Here you see an example of sums of exponential functions. The first function is just a bi-exponential equation. The second function with 3 parameters is a bi-exponential with an uptake and a clearance term, and the last function has 2 clearance terms but starts at 100 at time point 0, so it is well suited for the total body kinetics. On the right-hand side you see some a priori knowledge of what is known about these functions. It's known that the prefactors ai and the lambdas are positive, and that at time 0 the function values are either 0 or 100 in the other 2 functions. Also, it is known that we have lambda physics, which means we know the half-life of the radionuclide, and we know the number of exponentials in this case because we assume there are only 2 exponentials. An example of a compartment model which uses structural a priori knowledge is shown here. This is just the EANM SOP for pretherapeutic dosimetry of benign thyroid diseases. I will not discuss the model in detail here, but you see there is a structure assumed for the model and all the parameters are positive and so on. So there is a lot of a priori knowledge in this compartmental model. An example of a physiological model. Here I show a whole body physiologically based pharmacokinetic model. It has a global structure, and this includes many organs which are connected by the arteries and the veins. And you see on the left side that one can perform injections into this model. Every organ consists of many different compartments. Therefore, it can be quite challenging to develop and use this model. The advantage of such a model clearly is that there is integrated a lot of a priori knowledge about the anatomy and physiology of humans, and one can produce with it a digital twin or a virtual patient with which one can optimize the treatment of an individual patient. Population pharmacokinetic models. So up to now I spoke about the usual models everyone knows, but you can also use population pharmacokinetic models. These models use information about the parameter distribution in the population, such as the mean and standard deviation of a parameter. This can be performed in the Bayesian framework. That means the knowledge is added to the objective function when fitting the individual data points of a patient. This will be shown in the next webinar in the examples. Another method to use this information is nonlinear mixed effects modeling. Examples are presented in the webinar on population pharmacokinetics. Now we come to the model selection. So the question is which fit functions to use. Either you have obtained knowledge a priori about the best fit function, or, which is most often the case, you should have a good guesses and use a data-based model selection method. Model selection means one needs to choose an optimal fit function. What are the criteria for selecting a model? So first, clearly, it's the purpose of the model. Do you want just to calculate the area under the curve, or do you want to investigate the biological system more accurately? It depends also on the number and precision of obtainable data points, because this defines the maximum number of parameters you can determine. This statement is not valid if one can use population models. Maybe there is a model from the literature you can just take. Or it may also be that knowledge is available to be incorporated in a model like the PBPK model presented before. Also, one should apply the parsimony principle. For the model selection, I present the archaic information criterion here. There are more criteria proposed, but the AIC is suited and simple as seen in the equation below. The AICC value is simply the minimized objective function, which is obtained from the fitting the respective function, and then one just adds 2 times the number of parameters plus a small correction, because usually in nuclear medicine we do not have that many measurements. Then one calculates the AICC values for all functions or models one wants to compare. From these, one chooses the function where the AICC value is minimal. Then one calculates the delta by subtracting the minimum AICC value, followed by calculating the archaic weight using the equation shown at the bottom. This table presents quality control measures which must be performed before the AICC values are used to calculate the archaic weights. Visual inspection of the data and the fit curve are mandatory. The adjusted R-squared value and the plausibility of the parameter values are to be done qualitatively. The constraints for the standard errors of the parameters and the off-diagonal elements of the correlation matrix should be met. The weighted residuals should show a random distribution, as a systematic deviation indicates that another fit function may be needed, or at least better. Finally, the archaic weights for all investigated fit functions can be calculated and used for further calculations. So, how do we perform the model selection? First, create a model set containing suitable functions. Therefore, include a priori knowledge if it is available. Second, fit all these models to the individual data and use quality control for the fits. Third, calculate the model selection criterion for all models, that is, the AICC values. Fourth, calculate the archaic weights for all the models. Finally, select the models. The one with the highest archaic weight if it is larger than 0.99, and else if it is lower, you can perform model averaging using those models with an archaic weight larger than 0.01. Model averaging is simply taking, for example, the time-integrated activity for models A and B and calculating the weighted sum with the archaic weights. Attention! Selecting only garbage models for the model set will yield a best garbage model. So the model set should incorporate as much a priori knowledge as reasonably possible. Output data. Here I give the example for the time-integrated activities. Outputs for other measures should be presented analogously. To calculate the time-integrated activities, give the goodness of fit for the winners of the model selection, including the graphs for visual inspection. Here you see an example of why visual inspection is essential. All these four fits have the same variance, mean, correlation and regression line. The lesson here is always visualize the data. Obviously, only the left upper curve is a good fit. All the others either systematically deviate from the fit curve, or have outliers which should be removed before the fit, or should not be fitted at all as there is only one outlier producing the fit. So this is always needed and essential. If the visual inspection is okay, calculate the time-integrated activity for the winners of the model selection. Give the uncertainty of the result using error propagation from the fitted parameters to the time-integrated activities, as was published in the literature. Then you are done, maybe. So, what to do if the uncertainty of the result is too high? Then, if we look again at this scheme presented in the introduction, we can see what to do if the result is not precise enough. We can go back to the beginning and collect additional data or try additional models containing more a priori information. In nuclear medicine, it is usually too late to collect additional data. Therefore, focusing on models that incorporate more prior information is essential. Summary. There are relatively few data available for dosimetry in nuclear medicine. Therefore, the use of additional information to create the appropriate fit model is essential. The range of a priori information that can be used extends from simple positivity and range constraints for parameters to the use of physiological information and population pharmacokinetic approaches. A final remark. Whole-body PBPK models can be used to construct virtual patients or digital twins and thus optimize individual treatment in the future. Here are some links you may find of interest. Thank you for your attention.